Okay, so first thing we're going to do is derive the impulse momentum theorem. We're going to start with both Newton's second law as well as our first kinematic equation. Okay, so we're going to start off with our kinematic equation, and we're going to rearrange it to solve for AT, just to get AT on one side by itself. So we subtract V initial on both sides. You're left with AT equals V final minus V initial. And the second step, let's write down those steps. The second step is that we're going to multiply through by m, mass. So we'll multiply all factors in here by m. So we get m times acceleration times time equals mv final minus mv initial. Okay, well, we know that mass times acceleration, that is just force. And we know that m times v final is just momentum final. And we know that m times v initial is momentum initial. So we're left with force times time. We know what force times time is. That's impulse. And we know p final minus p initial. That's just the change in momentum. So this is our impulse momentum theorem. Okay, let's go ahead and do an example problem using this. So example number 1, a 2,200 kilogram car is traveling at 26 meters per second. So that's its initial velocity. The car is brought to a stop. So let's go ahead and write down our givens. V initial equals 26 meters per second. It's brought to a stop, so that means V final equals 0 meters per second. We want to know what is the average force in each case, so we're looking for F. Okay, well, we just derived this impulse momentum theorem, so we're going to want to start with that. And let's go to do A first. We're gently applying the brakes, taking 21 seconds to stop. So we're going to find what is that average force. So let's start with our impulse momentum theorem. So we know I equals delta P, which means force times time equals mv final minus mv initial. We want force, so let's divide through by time. We get force equals mv final minus mv initial divided by time. And we're going to use this same equation for B and C, because the only thing that's changing is time, so we don't need to derive this each time. So let's go ahead and solve for force. Well, we know that V final is equal to 0, so that cancels out this entire factor right here. So really our equation actually is force equals negative mv initial divided by time. Okay, so this negative is only playing the role that it's telling us it's the opposing force. It's the force that's stopping the car, for example, friction. Okay, so we're just finding the magnitude right now. Magnitude of force. So we get negative 2,200 kilograms times our initial velocity is 26 divided by 21 seconds. And we get a force of, plug that in your calculator, 2,723.8 newtons, which is approximately 2,724. Or written in scientific notation, it's 2.7 times 10 to the third power. So let's do this same exact thing 2 more times. So our second scenario is we're slamming on the brakes, taking 3.8 seconds to stop. So let's start with the same equation. And you can kind of predict that if our denominator is going to be smaller, a smaller number now, it's 3.8 seconds, then you can predict that our force is going to be much greater. Let's just confirm that using math. When you plug this in your calculator, you get 15,052.6, which is approximately 1.5 times 10 to the 4th newtons. So a much greater force to stop the same car in a smaller time period. So you can predict for our third scenario, where our time is 0.22 seconds to stop, that it's going to be a much greater force. So 2,200 kilograms times 26 meters per second divided by 0.22 seconds, you should get an average force of 260,000 newtons, which is 2.6 times 10 to the 5th newtons. So as the time decreases, force must increase if the velocity and the mass are staying the same. Okay, let's do one more example problem. So below is a force time graph for a baseball being hit by a bat. What is the change in momentum of the baseball? So we know that the area under a force time graph gives us the impulse. So we can calculate the impulse. We just need to find this area. Well, that is a triangle, so we can use our area for triangles 1/2 base times height. Our base in this case is 1, 2, 3, 4 seconds. And our height is 30 newtons. So you should get 30 times 4, 120 times a half, so you should get 60 newton seconds. So that is our impulse. We also know that impulse is equal to change in momentum. So therefore, they're the same amount. Okay, so second question, what is the ball's speed after the impulse is applied if its mass is 0.5 kilograms and it starts from rest? So we're going to use the same impulse momentum theorem. We know, since we know impulse is equal to change in momentum, that means our change in momentum is equal to P final minus P initial. Well, we know that the V final, we don't know V final. V final is what we want to know. We know V initial equals 0. We know mass is 0.5 kilograms. So let's solve for V final. So add mv initial on both sides. Divide through by m. You get V final equals delta P plus mv initial over m. And since we know the V initial is 0 meters per second, since it's starting from rest, that cancels out this factor right here. So we're just left with delta P over m. We know delta P. Delta P was 60 kilogram meters per second. And we know m. M is 0.5 kilograms. So our kilograms cancels. We're left with meter per second, and that makes sense because we're looking for velocity. And you get 120 meters per second as your final answer. For this next problem, go ahead and pause the video and try it yourself. And then you can either watch the video or just fast forward and check your answers. So now we have a 2,000 kilogram car. It starts from rest at a red light. So that means its V initial equals 0 meters per second. The driver holds down the gas pedal for 10 seconds. Time equals 10 seconds. Applying an average force of 375 newtons. So force equals 375. There's a few things that we need to solve for. So A, we are solving for impulse. Well, impulse is equal to force times time. So let's just multiply those two numbers together. 375 times 10 and you get 3,750 Newton seconds. What is the car's momentum after 10 seconds? Well, we also know from the impulse momentum theorem that impulse is equal to the change in momentum. So we know that momentum is also equal to 3,750, but now kilogram meters per second. We want to make sure our units align for what we're solving for. For part C, what is the car's speed after 10 seconds? Well, we know that the change in momentum is equal to P final minus P initial. And we're looking for the speed, so V final. We know it's starting from rest, so V initial is 0 meters per second. So let's go ahead and solve for, and I just went ahead and plugged in mv for momentum, So let's solve for V final. Delta P plus mv initial equals mv final, divide through by m. You're left with V final equals delta P plus mv initial over m. Since we know the V initial is 0, that cancels this factor out. So we're left with 3,750 kilogram meters per second divided by our mass, which was 2,000 kilograms. You get 1.875 meters per second.